Institute of Engineering and Technology.
Hello students, in this talk we are going to consider the second part of our Fourier series, which is Fourier series in a special case of even and odd functions by nature. What will happen in this talk is, suppose our function is not defined on only positive part or only negative part. If it is defined on a part which is equally distributed through our point origin, for example, suppose my function is defined over a symmetric interval with the center at origin from -c to c. What will happen to the integration? We know that if our function is odd by nature, then its integration over a symmetric range is always considered to be 0. And if my function is even by nature, then its integration over symmetric range is always considered to be double times or 2 times from any single part of that symmetric interval. So this is the reason why we can use or we can incorporate this particular idea of even and odd function into the Fourier series representation, as ultimately we are dealing with the integration in form of coefficients of Fourier series. So today's talk is all about how to incorporate that even odd nature of the function in Fourier series. Okay, so let us start our first part, that is Fourier series in case of even function. We'll divide this talk into 2 parts, first for even, second for odd function. So let us consider actually what do we mean by even function. So the algebraic check for a function for even or not is, if you replace x with -x in the function and if it remains same, then that function is known as even function by nature. And there is another check which is graphical, that if your function is plotted on xy plane and if its graph looks symmetric about y-axis, then we can say that it is even by nature. Now let us consider this second property, as sometimes we have graph available in the question. So if I consider this parabola, then it is known as symmetric about y-axis. Now symmetric about y-axis means if you consider y-axis, it will work as a mirror. So if you take one part of this graph, means on the positive x or the negative x or positive x, it will be reflected through y-axis. So y-axis will work as a mirror. This is another example of trigonometric function, a very fundamental function, which is cos function. You can imagine this situation in another way also. If I fold this particular page in which I am representing it through y-axis, then if I fold it, that new image will be exactly embedded on the other part. These are another possibilities. These are not any known functions, but these are combination of all random functions which will ultimately result into even by nature. So it may happen that your function is symmetric about y-axis and it is defined on some symmetric interval. So here almost in all graphs I have taken -2 to 2 range or -c to c range. It is very important that your symmetric range is given, then and then only you can use this nature. So whenever you have a symmetric range from -c to c, you can come to this part of even odd nature of the function. But if your interval is not symmetric, always go for the general case which we discussed in our previous talk. So now let us consider what will happen to the even function in Fourier series and what will happen to its coefficients. So if I focus on this talk, that my function is even function defined on -c to c, what will happen to value of L? See here, initial value is c, -c, and ending value is small c. That means the total length of this interval is 2c. That means capital L is equal to c. This is how you should calculate capital L. Capital L is nothing but half length of the given interval. So I am replacing every that value of capital L with small c. This will represent this Fourier series for even function. But now let us come to the coefficients. If I consider a value of a0, you can see it is from -c to c f of x dx. As my function is even by nature on symmetric range, I can replace that integrations range from 0 to c with help of even nature. So it will be 2 by c 0 to c f of x dx. So value of a, and similarly my function is even, cos function by nature is even, and we know that multiplication of two even function is even. So that resulting function f of x into cos of n pi x by c is ultimately even by nature, and so overall function is even. That means again I can reduce my range. But now what will happen if I multiply f of x with sine function? Sine is odd by nature. If you multiply odd function with even function, the resulting function will become odd, and that means my f of x into sine of n pi x by c is odd by nature, and that means on a symmetric interval it will result into 0. So this will reduce your work actually. If you identify the symmetric interval, you should always prefer that example first in exam, as it is reducing your work to find all different coefficients. So that means now my length of this Fourier series is reduced with help of only two coefficients a0 and n. You can find the answer. And in fact it is natural also that my function by nature is even function, so it can be represented by another function which is even by nature, and that function is cos. So remember, if your function is even, you can represent it by another even function which is cos. Now let us consider one example to practice this thing, how we can represent even function by Fourier series. Suppose my function is x square and my range is -1 to 1. So remember one thing, you should always focus on the range of the given function first. It is -1 to 1, interval on which it is defined -1 to 1. It is symmetric by nature. So and so I can come to the nature of the function. Now it is x square. If I replace x with -x, function remains same, and that means it is even by nature. So now I can directly implement my Fourier series for even function. So here value of c is equal to 1. C is nothing but half length of the given interval. And then we know that how to define Fourier series for even function. It is a0 by 2 summation n from 1 to infinity a n cos of n pi x by c. So now if I take value of a0, it is 2 by c 0 to c f of x. So it is 2 by 1 0 to 1 x square dx. Ultimately it will result into 2 by 3. Now coming to the next coefficient, which is an. Again I will take integration by parts. Remember, throughout this Fourier series you should apply always Leibniz formula in your calculation. So again I am using Leibniz formula where I am taking u equal to x square, v equal to cos x. It is a process in which we are taking two brackets at a time. First bracket is for x square, second is for integration of cos, and then change the sign. In first bracket take derivative of previous one, in second bracket take integration of previous second. This is the process which we are going to follow throughout this calculation, and stop wherever your first bracket contains constant value. And then take all these inputs 0, 1. So ultimately it will give you answer of an as 4 upon n square pi square minus 1 raised to n. Now let us take input of this 2 a0 and an in our series. So ultimately it gives you 1 by 3 plus n equal to 1 to infinity 4 upon n square pi square minus 1 raised to n cos n by x. Now if I change the value of n, it will give me the components of this series, and then we'll see how actually it is moving closer to the graph of x square. So remember, this is the Fourier series representation of even function over symmetric interval -1 to 1. So this is happening. See, I am taking a parabolic graph. This is x square for range -1 to 1. Now if I take my first approximation, that means in series I am taking n equal to 1. It gives me a first approximation like this. I am increasing the value of n. You will look that it will increase the fluctuations in your graph. So if I increase all such values of n, ultimately what will happen? All those fluctuations will become very small by nature, and ultimately it will move closer and closer to the given graph of parabola. Now let us consider second part of this discussion, which is odd function. How to identify whether given function is odd or not? Again, first algebraic check is if you replace x with -x, your answer is multiplied with minus sign at last. This is the notification that your graph or the function is odd function. Now the graphical representation of odd function is it is symmetric about origin. You can say a cross quadrant symmetry. A graph which is in the first quadrant, it is flipped to the third quadrant. Graph which is in the second quadrant, it is flipped to the fourth quadrant. Or you can say it is symmetric about origin. So if your function is odd by nature, this is how you can identify its properties. So these are some examples of odd function. You can see clearly here in the first quadrant, I am taking a graph which looks like a parabola. And then in third quadrant, it is flipped down. In second quadrant, we don't have anything. If there is something, it is flipped to the fourth quadrant. Like here, in case of sine function, it is odd by nature. And this is again some random graph. Here I am taking a possibility in all four quadrants. So you can see a small peak in that first quadrant, it is flipped to the third, and then a graph which looks like increasing graph in the second quadrant, it is flipped in the fourth. This is how you can identify whether the nature of the function is even or odd. Now let us come to the odd functions Fourier series and what are the coefficients. Okay, so if my function f of x equal to y is odd, defined on minus c to c, its Fourier series in general is given by this thing. Now coming to the coefficients, a0 will be 0. As my function is odd function over symmetric interval, its integration is 0. an is nothing but odd into cos function. So in an you have ultimately odd function defined on minus c to c. So that is also going to be 0. And finally whenever it will come to bn, it is odd function into sine. Odd into odd is even by nature. And that means overall function is even. So again it will reduce your range from minus c to c to 0 to c, but it is now multiplied by 2. So again your length is reduced for the Fourier series and now you are getting only bn, and this is quite obvious as we are now dealing with the odd function, and in odd function you can see clearly that here it is represented by sine. So now let me take one example. In example I am taking function f of x equal to 2x where x is coming from minus 1 to 1. So here again value of c equal to 1. If I take Fourier series for this odd function, you know that it is odd as I replace x with minus x, my answer is multiplied by minus 1. And so it is odd by nature. So now in Fourier series we have only that coefficient bn. So now coming to that calculation, in bn we have 2 by c 0 to c f of x sine pi x by c dx. C is equal to 1 and I am taking input for function f of x is 2x. So again it is x into sine n pi x. So again integration by parts, I am using Leibniz formula. So again first bracket is for x, second bracket is for integration of sine. Change the sign from plus to minus, take two brackets, derivative of previous first, in second bracket integration of previous second. Then take input 0 to 1 and ultimately it will give you minus 4 times minus 1 raised to n upon n pi. This is value of bn. So now if I take all these values into my Fourier series, it gives me answer for this 2x is minus 4 into minus 1 raised to n by n pi sine of n pi x. So odd natured function is represented by sine. Coming to the graph, this graph 2x in minus 1 to 1 is given by this straight line. So if I take first approximation, it is nothing but sine graph. Then I increase the value of n. So term by term I am adding more and more sine graphs into this calculation, and ultimately what will happen if you take infinitely many such calculations or infinitely many such values of n, your fluctuations will increase and it will move around that line passing through origin given by 2x. So I hope all of you now are pretty much clear about this idea of Fourier series in general case, Fourier series for even odd function, how to deal with coefficients in case of even and odd. I hope all of you will go for the enough practice for this case, as more you practice, more you will get idea about all these situations. So in this talk we considered a special case where we are taking even and odd functions. In upcoming discussion we are going to cover a third and the last part where we are dealing with the half range of the function. Thank you.
Institute of Engineering and Technology.